Hi everyone, this is Charles. So this video covers the part one problem which is in data 605 final exam. So the problem statement is you need to identify some of the probabilities which is mentioned here, and for that we need to build some of the random variables. So these are the instructions given in the problem to generate the random variable. So you need to generate two random variable. One is x. X has 10,000 random uniform numbers from 1 to n, where n can be any number of your choice greater than or equal to 6. And y is another random variable which has also 10,000 random normal numbers with a mean of n plus 1 divided by 2. So in my work, so I have created 10,000 um, random variable which is between 6 and n, where n is 100. And then I have generated another 10,000 random variable which has a standard deviation and mean equal to n plus 1 divided by 2. So I have made a summary of all these random variables, and then I have created the median and the first quartile of y variable, which is 16, and the median is 52. And the first question is to find a couple of probabilities. The first one is um, which is a conditional probability. So we can find the conditional probability x greater than median, given that x greater than the first quantile of y. So we can find the probability so using the formula or to find the conditional probability, probability of A and B divided by the probability of B. So we can easily find the statistics from the given data using this formula, and then you can find out this probability, and came up 0.56. And similarly, the second probability is to find so this is very similar to P, A and B. Similarly, you can find out the stats from the given data using this formula. And the third one is basically again a conditional probability which you can easily find from the test data using this formula, which came up as 0.43. Okay, and the second question is to investigate probability A and B equal to probability A multiplied by probability of B. So in order to do that, we need to build a contingency table using these formulas, and then I made a contingency table like this, and from that I can build a contingency probability table, which is basically this one, give you the probability of each and every permutations and combinations. So this middle one is called join probability, and the probability which are given on the sides are marginal probability. So using this one, you can identify probability of A and B, and probability of A and probability of B. So if you multiply probability of A and probability of B, you will essentially get probability of A and B. See, both are same. Okay, so from the contingency table, I can identify the probability of A and B, probability of A and probability of B, and multiplying probability of A and probability of B, you'll get a probability of A and B. Both are same, so it is proved that this formula is correct. Probability of A and B equal to probability of A and multiplied by probability of B. So the third question is to identify to see if the independence holds by using Fisher exact test and the chi-square test. So first I parse the contingency matrix to the chi-square. So it has two hypotheses to test. So the first hypothesis is a null hypothesis, and the second one is the alternate hypothesis where x and y are dependent. So we are trying to prove whether to reject or accept the null hypothesis. So looking at the p-value, um, it's greater than 0.05. Um, so we cannot reject the null hypothesis. That means x and y are independent. Okay, so let's do a Fisher test to find the probability p-value. So the Fisher test also gives you the same exact result. The p-value it's 0.799, which is similar to the chi-square p-value. So the basic difference between Fisher test and chi-square is basically um, uh, Fisher test is basically used for small samples or proportion, and chi-square is used for large samples. And Fisher test is basically it's intensive operation and highly computational, and it all always give you the correct p-value, even though it is even though you have a small data set or large data set. Um, Thank you. That's it for the part one explanation. Thank you.